Hello, and welcome to our Multimedia Applications and Virtual Reality course. This section details the visual immersion in VR. Visual perception may occur directly and naturally without any intervening interface, or it may be mediated, diffused, or delayed when the image is conveyed through peripheral devices. The entities perceived through screens can be either real or virtual. When virtual entities are perceived while completely disregarding their artificial nature, the user experiences total immersion. Conversely, if this perception is partial or filtered, the resulting immersion is necessarily limited. Visual immersion occurs when a user's perception is fully dominated by the virtual environment, effectively excluding real-world visual cues. Achieving this requires several technical and perceptual conditions. First, the display should cover almost the entire field of vision horizontally and vertically. A wide FOV, usually above 100 degrees, removes peripheral references to the real world and strengthens the sense of presence. Second, sharp, detailed images with high resolution prevent pixelation, while a high refresh rate, 90 Hz or more, ensures smooth motion and reduces flicker or motion sickness. Together, they create a stable, convincing visual experience. Third, delays between head or eye movement and the corresponding image update must be minimal, less than 20 milliseconds. Low latency keeps the virtual world aligned with the user's gaze, reinforcing realism. Fourth, each eye sees a slightly different image, creating binocular disparity and depth perception. Combined with motion parallax as the user moves, this generates a strong 3D illusion. Fifth, objects must follow real-world proportions and perspective. Errors in scale or distance can immediately break immersion. Sixth, the system must respond accurately to gaze and head movements, allowing natural viewpoint adjustments and maintaining visual alignment. Seventh, users should be shielded from distractions like light, room edges, or devices. HMDs, or immersive rooms like caves, provide this full visual enclosure. Finally, the virtual environment must be visually stable, obeying physical and spatial rules like lighting and object continuity. Any incoherence or graphical artifact can instantly break the illusion. Depth perception, our ability to judge distance and perceive 3D structure, relies on multiple mechanisms rather than a single source. While stereoscopic vision is the primary driver, several monocular cues also contribute, including image resolution and other visual hints. Binocular, stereoscopic vision, the primary mechanism. Each eye views the world from a slightly different angle, a phenomenon called binocular disparity. The brain fuses these two images to reconstruct depth and volume, which is especially effective at short to medium distances, up to around 20 meters. This principle is the foundation of 3D perception in VR, which is why headsets present two slightly offset images, one for each eye. Stereoscopic vision, therefore, remains the main source of depth perception. Monocular cues, complementary depth information. Even with one eye, the brain can infer depth using several visual cues. Motion parallax. Nearby objects move faster across the field of view as we move or turn our head. Perspective. Parallel lines converge in the distance, like a road narrowing toward the horizon. Size. Familiar objects appear smaller when farther away, such as a distant person. Occlusion. One object blocking another signals which is in front, like a tree hiding part of a building. Texture gradient. Distant textures appear smoother. For example, grass looks detailed nearby but blurry far away. Shadows and light. Lighting indicates shape and position, making a sphere appear 3D. Together, these cues allow us to perceive depth even on flat screens or photographs, complementing stereoscopic vision for a rich spatial understanding.
Let's talk about fixed stationary immersive interfaces. These are immersive systems where the user remains in a defined space and the virtual environment is presented through screens, projections, or specialized displays. They provide powerful visual experiences without requiring full mobility. First, caves, the immersive rooms. A cave, or cave automatic virtual environment, is a room-sized cube where images are projected on walls and sometimes the floor and ceiling. Users wear stereoscopic glasses tracked by motion sensors, moving freely inside. By projecting synchronized 3D images on multiple surfaces, caves create a strong sense of spatial presence. They are still used for scientific visualization, design review, and collaborative VR, allowing multiple users to share the same immersive scene. Next, immersive desks and workbenches. These are smaller projection environments, often with horizontal or inclined surfaces displaying 3D models in depth. Users view them through stereoscopic glasses, sometimes with head tracking and haptic feedback. They are ideal for semi-immersive applications like medical imaging, industrial design, and education. Now, large displays and projection screens. High-resolution screens or curved projectors can surround part of the user's visual field. While not fully immersive, they provide a wide field of view, commonly used in flight simulators, training systems, and panoramic installations. Let's talk about stereoscopic displays. These displays send slightly different images to each eye, creating 3D perception. They can be flat monitors, projectors, or TVs, using optical methods to separate the images. Parallax barrier displays are mostly obsolete. They use slits in front of the screen to direct pixels to each eye, allowing depth without glasses. Narrow viewing angles and brightness loss limit their use to small portable displays or research prototypes. Lenticular displays work similarly. Lenses refract light to send different images to each eye, creating a 3D effect without eyewear. Accuracy is limited, so they're mostly used in advertising panels or handheld devices rather than high-end VR. Moving on to glasses-based stereoscopic techniques. Anaglyph glasses, using color filters, are now mostly obsolete. They encode left and right images in complementary colors, typically red and cyan. Each lens filters one color, providing basic 3D perception but causing color distortion and fatigue, mainly used for educational demos. Polarizing glasses, still widely used. Polarized systems use light waves oscillating in different planes. Projectors emit light with different polarization, and each lens passes only one orientation. This allows spatial or temporal multiplexing, making it common in cinemas and large VR setups, supporting multiple viewers at once. Finally, active shutter glasses. These use liquid crystal shutters to alternately block each eye in sync with the display refresh. Each eye sees its image in sequence, producing full-color 3D. Once dominant in early 3D graphics and simulation, it is gradually replaced by HMDs due to comfort and synchronization limits.
Let's explore mobile and wearable interfaces. These are immersive systems that users can carry or wear, providing VR or mixed reality experiences anywhere. First, head-mounted displays, or HMDs. HMDs are the most common immersive interfaces in modern VR. They combine stereoscopic displays, motion tracking, and head orientation sensors in a headset worn by the user. By updating images according to head movement, they provide a real-time, egocentric experience. Examples include MetaQuest, HTC Vive, and Valve Index. Modern HMDs often feature eye tracking, pass-through cameras, and hand detection, enhancing both immersion and interaction. Next, smart glasses and augmented reality headsets. These devices overlay virtual content onto the real world using semi-transparent lenses or waveguides. Users can see and interact with both real and virtual elements at the same time. Examples include Microsoft HoloLens and Magic Leap 2, enabling true mixed reality experiences. Finally, smartphone-based viewers like VR boxes or Google Cardboard, now mostly obsolete. Early mobile VR used smartphones inserted into plastic or cardboard headsets. The phone displayed two side-by-side images for simple stereoscopic viewing. While low cost and accessible, these systems lacked positional tracking and interactivity, so they are largely replaced by modern HMDs. Let's look at emerging and hybrid interfaces. These are next-generation VR systems that go beyond traditional screens and headsets, exploring new ways to experience immersion. First, light field displays. Light field technology reproduces both the direction and intensity of light rays in space, allowing natural depth perception and focus changes without stereoscopy. Still experimental, it represents a promising future for natural, fatigue-free VR experiences. Next, holographic displays. Holography reconstructs the full light wavefront of 3D objects, enabling true volumetric perception without glasses. Currently used in research labs and prototypes, it points toward next-generation immersive visualization. Finally, panoramic dome projections. Also called full dome or immersive dome systems, these are large hemispherical projection environments that surround viewers with imagery on curved surfaces, typically covering 180 degrees to 360 degrees, creating a fully encompassing visual experience.